So I'm plugging in x equals -2. Truth be told, I actually don't care what the number is, what the value is. I only care if this is a positive or a negative number. I get a negative number, so I'm just going to say the second derivative is negative. Plugging in 1, again, don't really care that this is 18. I just care that this is positive, so my second derivative is positive. Second derivative is negative, means I'm concave down, so that means I have a local maximum. So I can say x equals -2 is a local maximum as the first derivative at -2 equals 0, and the second derivative at -2 is negative. That means x equals 1 is a second derivative is positive, so concave up. So again, so this is just exercising the second derivative test. So we don't have to do any algebra, solving for x, just focusing on that second derivative test. What can I say about the graph of f at x equals 3? Yeah.
Local minimum maximum. Local maximum is concave.
Yeah. So the first derivative at 3 is 0. So we're flat at that point. And the graph is concave down, so I'm tracing out a local maximum. So I can say f has a local max at x equals 3 as the first derivative equals 0, and the second derivative, again, don't care what the value is, just say it's negative. You said, why is that? Yeah. So if my second derivative is negative, that means concave down. Concave down is a friend. So I get a max.
Is that just a rule of thumb or your
No. That is the rule of thumb. If you're concave down is a frown. Well, if your first derivative is 0 and you live on a frown, you had to have been a maximum. If you lived on a concave up, so cup, and your first derivative is 0, that would have been a negative. All right, so let's see how we did.
And really, your first derivative is always going to be 0 because you're setting it to 0 to make it 0.
Yep. In order to be a maximum or a minimum, local maximum, local min, I should say, we have to be flat in the first place. So the first derivative is going to be 0. So we can see a local max at -2 and a local min at 1. Is it better with the lights on or off? On. All right. Questions about just Calc 1 side? All right, let's extend it to Calc 3 now.
Ooh.
So, same idea, it's still local extrema. So we have some sort of surface, some f of x comma y. We are still able to find local maximums and local minimums. It's just going to be of this surface. If I just go back to that analogy of, going on a hike, that local maximum is now the very top of the mountain, the peak of the mountain. So we're going to define critical numbers, critical points. So for Calc 1, we would just say, the first derivative has to equal 0. But here, it's not enough to say that I'm flat, because you have to be flat in which direction. To be a critical point, you have to be flat in both the x direction and the y direction. It means both your partial derivative in the x direction has to equal 0, and your partial derivative in the y direction has to equal 0. Another way of saying both your partial derivatives have to equal 0 is that your gradient vector equals 0. And remember from last time, the gradient vector is just the partial in the x direction, the partial in the y direction. So if we say the gradient vector equals, technically we should be a little more precise, since the gradient is a vector. We say it equals the 0 vector. 0 in the x, 0 in the y. So you just might see this as like the shorthand way of writing both of your partial derivatives have to equal 0. And what that's saying is your partial in the x direction, I have to have a local maximum at that point if I go in the x direction. If I sweep in the y direction, then I also have to have a local maximum at that point. Now let me show you just a quick example of why it needs to be true that both of them equal 0. And I need to be super clear. Both equal 0 at the same time. It's not a critical point where the partial in x is 0, but y is something else. And then another one where the partial in y is 0. This has to happen at the same time. If I just do something like this with my piece of paper, if I travel in this direction, then my derivative is 0. That would be something equivalent to saying the partial derivative with respect to x is 0, but then y is negative. So if I want this true maximum, it needs to be 0 in both directions. All right, so I gave us a surface here. Find all critical points. So to find the critical points, compute both your partial derivative with respect to x, your partial derivative with respect to y, and then we're going to set both equations equal to 0. You'll notice I'm kind of using the lazy notation now instead of writing like f sub x of x comma y. At this point, we'll see kind of online resources just write it this way. F sub x equals something. So now I want to set both of my partials equal to 0. So I've got 2x plus 6 equals 0. 2y minus 2 equals 0. So I have an x where my partial derivative of x equals 0. I have a y where the partial of y equals 0. Now, it has to happen at the same time. So if there was an x value that made this 0, a y value that made this 0, pairing them together, that is now a coordinate where both of my partials equal 0. Now, to classify that as a local maximum, a local minimum, or neither, we still have a second derivative. It's just slightly more complicated. So just peeking at that sheet, I think I use the real proper notation. It's the second derivative at some point. But really, this is what the second derivative test is saying to do. You just take your second derivative in your x direction, multiply it by your second derivative in the y direction, minus the mixed partial xy times yx. The only thing is, we learned that Clairaut's theorem says that these two mixed partials are actually the same. That's always true. So you'll always just see it written as one of them squared. So if we go online and we're like, well, hang on, he said xy, this says yx. Don't forget, those mean the same thing. So this quote-unquote discriminant is going to have three different cases. If your discriminant is positive, you have a local extreme. It's either a local maximum or a local minimum. If you get that your discriminant is negative, you have a quote-unquote saddle point. That is our neither scenario in Calc 3, and I will show us exactly what a saddle point is, and I think very quickly we'll be able to understand how it got that way. this is a critical point, and I will convince you that it is by showing you at the point 0, 0, my partial derivative with respect to y has a local maximum. If I go in the other direction, then I also get a critical point. This is a point where both of my partial derivatives with respect to y and x both equal 0. But it turns out in this direction, I get something concave down. So I'm thinking maximum. But now in this direction, I get something concave up, so a minimum. So it turns out in Calc 3, you can have a neither scenario. And it is a case where you have a critical point. The graph is flat here. If I'm on my hike, then I'm in a flat spot. But if I were to walk in one direction, I'm now walking downhill. But if I turn 90 degrees and walk in the other direction, I'm walking uphill. So this is, again, your neither scenario. We call this a quote-unquote saddle pole. And if we're wondering, how do we get its name? Look at that. Looks like a horse's saddle. It also looks like a Pringle. Some people call it a Pringle. And if your discriminant equals 0, then your second derivative test is inconclusive. What does that mean for us for the purposes of this class? Graph it. See what it looks like, and then report on it. Going under this first case, if the discriminant is positive, then it still turns into Calc 1. Check the second derivative values. This is saying if your second derivative is positive, so concave up, then you have a minimum. That idea doesn't leave us from Calc 1. If your second derivative is negative, then you get a local maximum. Still concave down, local maximum. Now, if we're wondering, well, I'm only kind of checking the x partial here, don't worry, that's already taken care of in your discriminant formula. And I'll just give you a quick preview as to what's happening here. If these were both negative numbers, then multiplying them, you get a positive. But if they were different in signs, then you get a negative. So it's kind of showing us what a saddle point would look like. Concave down, then concave up. And now this mixed partial is showing if I'm going in the x direction, how much am I pulling in the y direction, which a relevant example of that I will put up. So this is showing us here why it is not enough to only look at the partial derivative in the x direction and the partial derivative in the y direction. This is a case where the partial derivative in the x direction is 0 and concave up. Partial derivative in my y direction is 0 and concave up. So I'm kind of thinking minimum. But now if I were to look at some other trace, ooh, now I get something concave down. This is actually not a minimum. This is a Pringle. This is a saddle point. So our discriminant says it's not enough to just check these. You also have to check to see how much you're changing in the y and then x direction. So to sum it up, you've got 3 cases. And yes, we're going to do plenty of examples. We're going to find a critical number, like we just did. You're going to plug it into the second derivative, into the second partial for x, second partial for y. Plug it into your mixed partial. Once you've plugged that value into this discriminant formula, you're going to land on 3 cases. You get a positive number, boom. You found a local max or local min. If that's true, you can just check your second partials. You get a positive number, minimum. You get a negative number, maximum. If your discriminant is a negative, you got a saddle point. That's our weird neither case. It's a critical point, but just not a maximum. And then the last one is the second derivative. Excuse me. If the discriminant equals 0, then this test that we're doing doesn't work. For us, you got to wrap it. All right. Let's go ahead and let's now plug in -3, 1 into our discriminant. So looking at our formula over there, we need all of our second partials. So usually what we do when we start these problems, if it asks us to identify, then not only am I going to find my first derivatives here, I'm just going to find all of them right at the beginning of the problem, because I know I'm going to need them. So I'm just going to write them all up here. I'm going to have fx, fxx, fy, fyy, fxy. You also could have found fyx, but it's going to be the same. What you could do, and actually what I will do here, is find fxy, then fyx, and just know that these answers should be the same. And if they're not the same, I messed up somewhere, I need to go check. If I take the derivative of the partial in x, and then take the derivative with respect to y, there is no y. Stare at that for a second and make sure we're convinced as to what I'm doing here. I'm just dropping this into my formula. You're taking the critical point that we found, plugging it into your second partial for x, plug it into your second partial for y, minus your mixed partial squared. So I got the discriminant is 4, it's a positive number. Boom. I know that the critical point that we found, if I were to graph this surface, is now a local maximum or a local minimum. And now to check, I'm just looking at basically this first entry here. That's kind of why I write it that way. You're just looking at this. Was this positive? Yes, it is positive. So concave up. So it turns out this critical point is a what? It's a local minimum.
And we're only looking at the x,
So it turns out, if you check the x or the y, it's going to be the same thing. So you just need to check one. All right. And I, of course, can pull out the projector and convince us. So sure enough, graphing my surface, I do see a local minimum. We said that this happens at the point -3, 1. But how can I get Desmos to display this point on the surface itself? So you could have done two things. You could have just said, well, what is the z coordinate when I plug it in? Or you could have just told Desmos, then graph f of negative. So make sure we're reading the language of the problem. If it says, what are the coordinates of the local minimum, then you want an x, comma, y, comma, z. So if we want to kind of convince ourselves exactly what this means if x equals -3 and y equals 1, and I look at those traces there, then it, both in my x direction and in my y direction, I've got a local minimum. Questions? Let's do one more together. Find all critical points and classify them. So, as I kind of mentioned in this middle section over here, we know the second derivative test calls on all those partial derivatives. So before I even start the problem, I'm just going to just compute all of my partial derivatives. This is just my scratch work getting ready to classify it at the end. But while I'm in the habit of taking derivatives now, I'm just going to find all of them. So critical points are where both the first partials equal 0. I'm not saying these are going to get entirely crazy, but will it always work out to be like, oh, you get x equals 2, y equals 1? Unfortunately, no. So you're going to have equations that have both x and y in them. So maybe over in this equation on the left, I'm going to solve for y. Because y is not the thing being squared. I don't have to take any square roots. And I get y equals x squared. So this is saying that your partial derivative with respect to x will equal 0 when y is x squared. Well then, why don't I just plug this into this partial over here and solve? So now over here I can just plug in y equals x squared. Now it just turns into some algebra. So I've got 3x to the 4th minus 3x equals 0. See? Yep, I recognize there's a 3x in both terms. Now I can set both of those factors equal to 0. So I'm just going to remind myself that y equals x squared. That was the thing that I plugged in. So if I have x equals 0, then what is the y coordinate of that critical point? cube roots, you do not get plus or minus. Only the even roots you get plus or minus. On one end, you get 1. So now I'm going to give you guys about a minute head start. Now you have 2 critical points. Run through your second derivative test. Classify those points as a local maximum, a local minimum. So I'm just dropping it into my discriminant. I've got it on my reference sheet. I'm going to plug 0, 0 into both my second derivatives for both x and y, second partials. This first one, I get 0 minus 9, I get a negative number, boom, saddle point. I can just stop there. The next one, I get a positive number, and be careful, you're not looking at the value of this to determine local max or min. You now have to check this value. Because this was positive, I can say local min. Another thing to mention, if the question says, find all coordinates of any local extrema, that is not saying the same thing as all critical points. Because this coordinate, 0, 0, is a critical point, but it is not a local extrema. It's not a max. So just be careful, pay attention to the language. If it says find local extrema, it's saying only the maximum. Alright, let me graph this, show you what it looks like. And we got some text. So this is my surface here. And we can see the red point at 0, 0 is a quote-unquote saddle point. The surface is flat then. If I walk along this direction, I'm going to go downhill. But if I were to walk along this direction, I'm going uphill. So my red point's a saddle point. But my blue point over here definitely is a local min. Questions? So both of my partials need to be 0. This equals 0 when y equals x squared. Well, to find the value over here where that's true, if I plug in y equals x squared, I can now find the values of x where the partial of y equals 0.
Do you just do that normally, or do you have to plug in?
What do you mean?
Like, does it solve it by itself without plugging anything in?
Oh yeah, sometimes we will get something we solve and then boom, x equals 2. You could solve this and get y equals 2, even though it's in the x direction. But now I'm saying that x equals 0 is what makes both of these equal 0. And by plugging x back into y equals x squared, I now have an x where this equals 0. And a y where this equals 0. So now I've got one for each. All right, go ahead and stand up, grab a marker, grab a circle board. The only thing that's going to bother us is just the algebra, the factoring, things like that. Okay. But what is the key?
Oh my gosh, we ain't even noticed that, that's a blazer.
took one aspirin. I think I should have took two.
That's the dead one. That's not in there.
You're taking the derivative of y. Then
Yeah, the X isn't zero.
so your x then y should be the same. So you should have a column for like your partial x.
I'll think about that one right now. This is okay here. So, just move over to the page.
I think we just maybe we have two x's.
Oh, wait.
Oh, you're on the back. You're on the back. I mean, it does not matter the order, but I was just expecting to see the first one. I would just, while you're at it, just find all of it. Just while you're in the swing, just take it apart.
So we have. Now we have to do.
Oh, I think he.
Or you're putting it in here. Zero.
Oh,
Yeah, do that.
Oh, I was
So what did you see, like, you take the X and just make it N?
We can do, okay, I can know.
Like, it doesn't matter what this is, like, it's being negative. Because this is zero. Yeah.
What's the derivative of like 6x? So that constant comes along. So if y squared is the constant, that comes along.
Then I have a provide an value that says 0, x, 0, right?
Oh,
It needs to be a derivative
You
of
got
1.
one more thing you have to do.
Doing it like this.
That's, so,
I got
X.
negative x
Right.
one, that's a
And after doing that,
You take the partial derivative with respect to X.
Either way,
Then take the partial derivative of this.
Everything
So you
derivative.
already
Yeah.
partial X.
and then do it both sides.
Do it on both sides, and you should verify that you get the same answer. Now over here, it's Y, then
That one, the order doesn't matter. This one doesn't matter.
so for Y, that would be.
Shit, can you see my board? I guess you can sort of
So 2X.
see me a little bit.
Yes,
I ain't doing too bad. I ain't doing too bad.
I don't think it's fantastic. Oh, yeah.
now that I figured out how to do this,
Well,
stop.
Literally just like
Why?
say yourself, like, pretend this is a thing and keep the derivative of x.
you're just doing the chain rule now.
I don't know what two steps, but I forgot what
Because now this
Step
is
is
everything. It's just a constant.
No, I know.
Right.
And I'm just like, well, I don't know how to do it.
Yeah.
Oh, shoot.
You got it? Nice.
Yeah,
So now we have to plug it into that second derivative.
Okay, and now, so, this is where so I'm plugging this into my ABED. Okay, and then even the FXY, I still plug that in.
He's the smartest man I know, so. He's like, oh, it's so great.
I was paying attention because I just got a migraine today, I'm sorry. Hey, hold on, I just went through all this all day.
It's only the negative.
He told me he became a professor by
That's cool.
I walked into a conference and I was like, oh, I guess I should do this in America now. Became a professor.
Oh, what the fuck is this? Well, that's it, that's all I got. I'll be in what X is all in. This stays the same, that's all. Who is this? But take the root, this, that's, so my, this is the base plate, two X. Alright, that's it, that's all you really want.
Okay, then what we do is, how long we do this? Also, this is first.
Oh, we know this is the product room now. Shit. What's that, dude? What's that, dude? This is the product room.
It is.
Is that what you saw?
Yeah, I hate this.
Okay, now, you plug this in, right, I got it in, now, so this is my, so that's my, this is that, now.
Everyone loves football, that's the only reason.
When you plug in to -4.
Okay, plug 2 negative 4 into this equation here,
I kind of like.
okay, represent, okay.
It's like, it's just this, so it's like F prime of X, F, then G of X, then F of X, and then G prime of X. So, derivatives stay the same, stay the same derivative. It's even. Yeah.
graph of e to the anything. Whenever you're solving, you've got e to the
Well,
something.
after I'm saying,
You don't
oh, we
have
know.
that. The other thing, if you wanted to know when this e to the x equals 0, if you took the natural log of both sides,
Literally back again.
and you get ln of 0, which is so it's an algebraic way of showing you, but don't worry about it.
But we can't get this to zero. You could just say, like, you could just kind of pretend like we did. Feel like, oh, how could I set this to, you know, I set this to zero. You can't do that. It's just kind of like, yeah, and then now with x zero.
Oh, but still, that's still two.
X is 2, y is
Yeah.
Right, so I should, yeah,
So this is, right now you're solving for f of y, f of y. This is just really slow for big guys.
So, yeah. Okay, wait, okay, so, yeah. What goes here? So it's gonna be the
Hold
same.
on, make sure.
See my. Okay, now.
What, you're doing f of y right now. That's what I'm trying to tell you. You're doing it right now. This is f of y. You're doing it right. That way.
So then what is f of y x?
Now I get to do
So,
this.
it would just be take this and then take the derivative. But no, if you're doing f of y,
Oh,
you
okay,
take all of
well.
this. Yeah, this is f
Just
of y.
erase.
Yeah, this erase that. Yeah.
Down to 0, 0,
You're doing f of y,
or you can just look at this thing.
Is the derivative of this.
Oh, so
Same thing as
okay.
0.
And that's the derivative of this with respect to x.
No.
Yeah.
No. E. Yeah, this was multiplied by something that was 0, so you can just say that. But this is just multiplied by negative 2. Just like that. Let's just get like an e to something. Create an calculator.
Find your critical set, your first partials of
Is this right for the f of x?
Yeah, so that was me.
So yeah, remember the f of y x, and take this big thing and put on here. But now just find the derivative of the inside with respect to x, which is just.
Am I supposed to be getting 0 out of this equation,
Just
or?
basically, I like to do it, keep this
For
the same,
the final thing?
Yeah.
keep this the same, and then take.
So this is actually
This is like the
storing my
coefficient
24.
of
Did I
that.
have my?
This all stays the same.
I'm doing it.
So right. Okay, but that's.
So this is the thing that you.
This is negative 24, but
But then you also have to find the derivative of this.
Right.
Yeah, which you already found, so really it's flipped, because first you find the derivative
Yeah,
of
pretty much. Because
y,
even this.
and now you have to find the derivative of this with respect to x.
Ah, I see what you're saying right there.
Yeah,
So
whatever
you
I
have
do.
to look at the.
Negative 20, negative.
partial derivative of y is 0, this would be 4.
It wouldn't be
Oh,
negative. Or negative 4. Yeah. So they have to be.
Square root
care about
negative one.
for the most part. Positive.
Yeah, just about it.
That's one thing we need to worry about. I don't need to worry about what it is.
So this
That
is
means it's extremely rich.
so you can set each of these.
Now we
values.
have to say
But we might remember
if
equally
that part is
anything
negative,
that
then
were
we're
equal
down
to
positive.
if you can
Wait, positive is positive, negative is down.
not putting in zero. You are saying.
So then it's
So you can set each of the factors.
okay, so then you have to.
I feel like. Should I do the last one?
Oh, yeah.
Or do you want me? We're just looking ahead. To make it fair. To make it fair. I'm not gonna go through this whole thing. What?
Yeah.
It never is. You can just ignore it.
I was looking ahead, it feels like it's gonna be. Take it, I'll let you take it. Yeah.
Alright, when we come back on Friday, don't worry, we're gonna do a little bit more of this. It is just algebra that needs practice, it needs repetition. We're gonna do a little bit more of this on Friday before we start our next lesson.
Okay.
And you can put the answers for these on.
I don't know.
Okay, I'm busy. Imagine you're teaching yourself.
And even took away my headache. Because I just need to think a little bit.
Like,
Yeah. Alexa, I need your photo for the math bulletin.
Yeah.
I think.
And then
You could also, like,
I also need your photo for the
It's really good.
Would you like your photo?